you hear me? Yes. Okay. So, hello everyone. My name is Edward Eaton. This is quantum collision finding in non-uniform random functions. This is joint work with Marco Bello and Sang Song at Portland State University. So, sometimes in cryptography we like hash functions, and in this talk, the domain of a hash function is always going to be represented by m, or its size is going to be m, and the codomain is going to be represented by n. And sometimes we want these hash functions to be collision resistant, which is to say that we don't want to be able to find two things in the domain that map to the same point in the codomain. So we want to be able to estimate how difficult it is to do exactly this. But there's a bit of a vague question about what we actually mean when we say difficulty. We might mean how long it takes. We might also incorporate, for example, space requirements, how many bit or qubit operations if we're considering quantum attacks, and whether we mean logical or physical, how easy any algorithm we're using is to parallelize, or just how many queries are needed to the hash function. So for this talk, we're only going to focus on the last metric, hash function queries. That's not to say that the others aren't incredibly important, just that it's easier to, in general, prove results about the number of hash function queries required, and it's easier often to actually incorporate those results into other proofs. So when we move into sort of a quantum world, then we can think of an adversary who has implemented a hash function on a quantum computer and may be able to sort of run it in superposition, which sort of gives us the idea of this sort of mapping where the output of the hash function is sort of spit out onto the second register there. So we're going to always think, so for this talk, we're going to think about generic security of hash functions. So this is where we kind of model the hash function as a black box that an adversary is querying and trying to find results on. So in general, the adversary is going to send some message or some point x and get back h of x. And then the adversary's goal will be to find two messages that map to the same point, a collision. Or when we think about a quantum adversary, they instead are querying a unitary with superposition, getting back a superposition. However, they still have to output classical information, and so they're still looking for a classical or a, collision in the same way. So thinking about the collision resistance of a hash function in terms of hash function queries, as long as our domain is sufficiently large, we can sort of guarantee that there probably will be collisions. And if we consider just sort of a totally uniform hash function, then we know that any algorithm that finds a collision in H with constant probability must be making about n to the 1/3 queries to the unitary. And in fact, there is an algorithm that does it in roughly n to the 1/3 queries. This is of course, analyzing collision resistance of a hash function has been analyzed a long time for cryptographic purposes and for uniformly random functions. I believe it was first done by Mark Chandry. So we can completely characterize the collision resistance of a hash function in terms of just the query complexity as n to the 1/3 for uniform functions. But there's also a question about, should we only be considering uniform functions? Might we want to ever consider non-uniform functions? So uniformity is actually a very strong condition on a function, so we may want to consider non-uniform functions just to be able to relax our assumptions when we sort of start modeling these hash functions as a generic black box. And then also occasionally things pop up that definitely are not uniform functions. For example, often composing uniform things with other things results in functions that are overall not entirely uniform. This has particularly relevance to proofs of Fujisaki Okamoto, which of course is very needed in a lot of CCA2 conversions, where you have sort of want to consider the collision resistance of some function f, which is sort of has to do with the encryption, and a hash function, and you want this overall composition to be collision resistant. So for modeling our non-uniform functions, we're going to be talking about min entropy. So the definition of min entropy is just you consider the For any distribution D on our codomain N, you consider what is the most likely element to be picked out, and you consider what is the probability of that to be picked out, and if it's 2 to the minus k, then you have min entropy k. And then we say that a hash function h has the distribution D if h of x has distribution D for every single point in the domain, and they're all independent. So this is kind of how we're going to model our non-uniform functions. Okay, so as an example, this is a distribution on 8 elements. So in this case, we have a uniform or flat distribution where every single element is equally likely. And here's sort of a more messy distribution. So in this case, so in these examples, the relative width indicates the probability of a color being picked. And in both these cases, we note that the most likely point it has probability 1 over 8, which implies that both these distributions have min entropy 3. We can also think of somewhat crazier distributions. So for example, distributions where there is one element that's maybe relatively likely to be picked, and then quite a few elements that are negligibly likely to be picked. So you require a very, very large codomain in this case. But it still just has min entropy 3 because the most likely element to be picked has probability 1 over 8. So in our analysis, a useful tool is going to be the collision probability, or actually 1 over the collision probability. So this is just the probability that when you sample 2 elements from the relevant distribution, that they're the same. And negative log beta is actually called the collision entropy. So for example, looking at some of those distributions that we saw before, the collision 1 over the collision probability for the uniform distribution is just 2 to the k. That's just because you pick any element and the probability of hitting that element again is 1 over 2 to the k. For this sort of delta distribution, we call it, it's somewhat close to 2 to the 2k. And that's just because you kind of have to consider the only way that you're going to get a collision is on that one element that's sort of much larger than the rest, and so you have to hit that twice. So 1 over 2. So 1 over 2 to the k and 1 times 1 over 2 to the k. And then for any sort of generic min entropy k distribution, you're kind of looking at somewhere between those two. Those are sort of the two extremes. So this has been analyzed before, looking at sort of for these different distributions, what kind of upper and lower bounds can we characterize. To our knowledge, the delta distribution hadn't been completely analyzed. That's not to say that it's, was a really hard open problem or anything. I just think no one had looked at it yet. But as said before, for the uniform distribution, we had this very nice characterization of 2 to the k over 3 and 2 to the k over 3. So we kind of want to fill in the rest of this table and hopefully get equally nice distribution. So in some previous work by Unruh et al., a generic min entropy k distribution was found to have take at least 2 to the k over 9 queries. So there was some independent work done from ours that analyzed a lot of the same problems that we were trying to analyze and had a lot of similar results. So, we weren't crazy. And Ebrahimi and Unruh found that, for example, for the delta distribution, it takes at least 2 to the k over 2 queries. It can be done in 2 to the k over 2 queries. And then they updated that 2 to the k over 9 for generic min entropy k distributions to 2 to the k over 5. And also analyzed how long it takes generic min entropy k distributions to find a collision in them. So in our work, which was done independently, we kind of update this a little bit. So in that delta column, we didn't have fundamentally different results. It was more just that we were considering different ranges of m and n. So we mostly got the same result there. However, notably, we have updated this corner of the table to 2 to the k over 3. That is, for any generic min entropy k distribution, it takes at least 2 to the k over 3 queries asymptotically, which is very nice because it kind of matches what we actually know as the lower bound with uniform distributions. So this can't be really improved, at least with respect to just considering min entropy. So for the remainder of this talk, I'm mostly going to talk about that one result, that it takes at least 2 to the k over 3 queries in a generic distribution. So We prove that any adversary that can find a collision in a hash function h primed, which has this generic output distribution of min entropy k, in q queries to the relevant unitary with probability p, can be used to find a collision in a hash function h with a uniform output distribution in 2 q queries to that unitary and with probability p over 2. So there's sort of a tightness gap of 4, which sort of disappears in the asymptotics. So we prove this by sort of doing a standard sort of reduction technique. So we sort of put that adversary in a black box and have them interact with an oracle h primed, which we are maintaining, and which we maintain through use of queries to h. And then we show that when the adversary spits out a collision in h primed, we can use that to spit out a collision in h. So the general proof outline is going to be that we're going to sort of chop up the uniform distribution and in order to turn it into the actual distribution for the adversary. So then we will show that a collision in the generic distribution should imply a collision in the uniform distribution. So to simulate that h prime distribution, we imagine that we have some sort of uniform output distribution. So we have access to a hash function h and its outputs are uniform. Let's say we pick some point totally random in the domain and we hash it and we get that sort of nice peach color. This is a hash function that spits out colors. We want to provide the adversary with access to a hash function which has this much more complicated distribution. So when we compute that the hash of the message is that nice peach color, we're going to choose what h primed of m can be based on this. So when we kind of line up these distributions, we can kind of think about how we want to properly chop these up. Of course, you could line them up in any way you want, but you know, we show that it doesn't really matter how you line them up. You can still get these nice results. So we just pick whatever way you want. And then let's zoom in on the section with the nice peach color. So the idea is going to be that when we are computing h of m and we get that it's nice that peach color, we're going to set h prime of m to be either that light pink, magenta, or teal color. So to choose which of these, we're going to need another randomness oracle, which is going to sort of take a point in the domain and then just sort of spit out a sufficient amount of randomness for some definition of sufficient. And note that querying this R oracle for more randomness doesn't actually require us to query H at all. So when the adversary then queries that point M, we're going to compute H of M, obtain a sufficient amount of randomness by this R of M, and from this decide what H prime of M is going to be by breaking up the H of M distribution, the uniform distribution. And this whole process, classically at least, only requires one query to H. And then note, if the adversary finds 2 points in the codomain, or sorry, in the domain that hash to the same thing with H primed, then we should have that H of M1 is equal to H of M2. But we don't actually always have this property. That was only for sort of the peach example, so we should need to look about how these things line up a bit more carefully. So let's look at that nice purple and I think that was forest green. So say the adversary finds, basically the problem results when you have sort of a point on the border. So say the adversary finds an M1 and an M2 such that H prime of M1 is equal to H prime of M2 is equal to that sort of pinky purpley color. Then we have to ask, what does this actually mean for H of M1 and H of M2? So we could have sort of any of these 4 possibilities. We could have it that that they're purple or green or purple and purple or green and green or green and purple. However, when we think about this, we can note that basically the adversary is not actually provided with direct access to H. They are only provided with access to H primed. And we're kind of assuming this because of how H is just sort of modeled as a uniformly random function. So when we don't give the adversary direct access to H, then the adversary has no ability to tell which case they are in when they find a collision. And so we can kind of argue that basically we're going to have, roughly speaking, something sort of uniform or depending on how the distribution works, sort of random across all these 4 possibilities. And then working through the math, you can spit out basically the case where that sort of pink color lies exactly in the two ranges is the worst case scenario, and in that case that you have that the probability that the adversary's collision translates to a collision for you is 1/2. And that's the worst case scenario. Other than that, you always have sort of a better probability. And the probability of this calculation is taken over the randomness oracle and any of the adversary's internal randomness. So we also need to think about how we simulate the quantum version of H primed. So for a quantum-enabled adversary, you have to quantumize the whole process, which means that you have to take in this sort of generic input psi with a superposition, and then we can make a quantum query to UH to get the quantum response there. Then we can pass the message register part of this through our randomness oracle, which we will also have a quantum version of. And this will obtain the randomness that's necessary to break apart the uniform distribution. And then we pass this result into a quantum circuit that breaks apart the uniform distribution, and we get the desired min entropy K distribution. And then we have to perform any sort of garbage collection, make sure that we don't sort of end up entangled with the adversary or something, and pass the result back. So sort of modeling this as a quantum circuit, we have sort of our message register X and Y, and then we require some auxiliary 0 there. We pass it through our whole process R, which sort of samples the randomness and then also converts the distributions. And then we pass through H again. That's just to uncompute that stuff so that we don't get entangled with the adversary. And then we can pass the result back to the adversary as a query to UH primed. So then we note that for each query the adversary makes to UH primed, we make exactly 2 queries to UH, and that was to uncompute some stuff. And that the function H primed has actually exactly the correct distribution as long as we are able to get a sufficient amount of randomness from R. So because of that, we sort of have that our adversary is going to find a collision with probability P. And this collision, as we said, will correspond to a collision in H with probability 1/2. So since we know that 2 to the k/3 queries are needed to break the collision resistance of H with constant probability, we get that the adversary needs to make at least 2 to the k/3 queries to H primed asymptotically. So there's still some open questions. For example, this process isn't necessarily efficient, breaking up the distributions. These distributions, of course, are intended to be quite large, and so it'd be nice to find ways to make that distribution conversion to be a bit more efficient. We also have to consider it would also be nice to consider cases where we aren't able to entirely characterize the distribution. And it would be also nice to characterize some of those lower bounds in terms of beta rather than just the min entropy, so the collision entropy. So to summarize, our main results were finding a collision in min entropy K distributed hash functions, take 2 to the k/3 quantum queries. But we also looked at several other things, which I'd just like to quickly highlight now, which includes that there exists min entropy K distributions that take 2 to the k/2 queries to find a collision. There exists an algorithm that finds a collision in min entropy K distributions in beta to the 1/3 queries, so we actually show sort of an upper bound there. And then we also took some time to analyze pre-image and second pre-image difficulty on min entropy K distributions and showed how we can also characterize these with beta and analyze them with these distribution conversions. Thank you.
Okay. Any question or comment?
So there are many applications in which you are trying to find a collision, not in a single function f, but in 2 functions f and g. You are trying to find an x and a y, such that f of x equals g of y. In the uniform case, there is a very old trick how you build one function, combining them, and then you try to find standard collision in the single combined function. Have you considered what happens to your analysis if you try to find a collision between one function f and one function g, where each one of them has a different distribution?
No, we did not consider that. So this is where you have 2 different functions you're trying to find collision. That would be very an interesting thing to consider, but we haven't so far.
Thanks.
Any others? Maybe I have a fundamental question. So your analysis is based on the non-uniform distribution of hash function, but why is Fujisaki Okamoto transform is non-uniform distribution?
So it shows up in Fujisaki Okamoto because you have this sort of composition of two functions. One function which is sort of related to the encryption process, and then applying a hash function, or applying a hash function first possibly. And then basically we can see that because the hash function itself, we're probably going to model as a random uniform function. And so as long as we do anything, then at that point, probably the overall process isn't going to be necessarily a uniform function, although it may be difficult to distinguish from that from a uniform function.
Okay, any others? If no, let's thank